amazing. We haven't even done anything yet. So, good afternoon. This is GopherCon. So let's give a serious round of applause to the organizers and to all of the people who are sponsors and, most importantly, the people who put this conference together. Put your hands together for them. It's been a really great conference so far. So I'm dead program. I'm going to have to keep looking over here. There's no courtesy monitor. I don't even know what I'm talking about. So I'm dead program, the ringleader of hybrid group. This other guy here is Zankich, in the real world Adrian Zankich, but that's not very important. He's the serious programming guy at the hybrid group. So he does all the work, and I take all the credit. It's kind of nice. I like it. Management. So we're with the hybrid group. We're a software development consultancy based in Los Angeles, California, home of the flying space robots. And if you're a fan of either the Jet Propulsion Laboratory or SpaceX, you know I'm not making this up. We're also the creators of Kids Ruby, which is won the Fukuoka Ruby Awards and gets about 1 terabyte of downloads a month. So if you want to teach your kids programming, starting around the time they can type, Kids Ruby is great. But today we're here to talk about Golang-powered robotics. I thought this was Electra, but it's actually Maria, and she leads a robot revolution. But that's outside the scope of this talk. So by its design, Go proposes an approach for the construction of system software on multi-core machines. And if you've read the Golang FAQ, you know that. But then there's one other little thing, which is what the futurist and author William Gibson said, which is the street finds its own uses for things. So that's what this talk is all about. It's about Gobot, which is a Go framework for robotics, physical computing, and the Internet of Things. It supports multiple hardware devices, different hardware devices, and multiple different hardware devices at the same time. God, I love Go. So here's a little bit of our system architecture, since you need a system architecture if you're going to have some kind of system. So our primary thing that we care about is, of course, the robot. And we're using a couple of very important design patterns. One of them is the adapter pattern. Similar to the way an object relational mapper allows you to write a single set of code that can talk to different kinds of databases. So we have what we call in Gobot connections, which is when you're talking to a particular piece of hardware, it goes through these adapters, which can then integrate and talk to different hardware, either using a serial interface, a socket to serial interface, or something even more esoteric, and then talking directly to the actual hardware. So it's a kind of hardware abstraction layer. Then we are using the adapter pattern, a double adapter pattern, if you will, with devices. So devices where a connection is to a particular piece of hardware, like a Raspberry Pi or a BeagleBone Black or an Arduino. Devices are things like buttons or LEDs or digital accelerometers. So our devices have drivers which allow them to share the connections. In other words, the same LED driver will work on a BeagleBone Black or Raspberry Pi or any number of different platforms. So that's a really important idea. Then we're also using the publish and subscribe pattern. When events occur that are detected by these different devices, they then notify the robot so that we can do things, pushing buttons, detecting collisions, launching attacks, whatever you want to do in your code. So a robot that's connected to the internet would be no good without an API, of course. So applications can communicate using our API with something we call the Master Control Program, or the MCP. So you can either use a RESTful HTTP style of interface, or you can use WebSockets or server-side events. So and there's other protocols that we're adding support for, like MQTT. So you communicate through the MCP, and then you can talk to your entire swarm of robots. We'll see some of that in a minute. Test-driven robotics is another one of the themes. If you own a Toyota like I do, you wish they had used that. But if you're designing a sprinkler system that's supposed to go off once a week, you're going to need to do something to make sure it actually works without waiting an entire week, unless you're Toyota. So command line interface. You don't want to be using GUI tools to configure your hardware. We actually have an entire separate project called GORT, which is a programming command line interface with all the different tools that you need for robot ops. And Robot Ops is DevOps for robots. It's another movement that we are trying to start. Go to our website, robotops.com, to participate. But this talk's not about Robot Ops. It's about robots. So let's see a demo. You guys came here to see some real robots, right? So of course we start with an Arduino. The Arduino is kind of the minimum viable microcontroller. They sell them at Radio Shack. Probably everybody here has 1 or 2 or 10 stacked up somewhere gathering dust. So let's take a look at some code too. Hopefully. Let's see what happens. Yes, code. All right. So forgive me that I have to kind of squint and lean. So this is a very simple Gobot program. Of course, it uses the main package, and we import the Gobot package, which is kind of the main framework, and then each of the different adapters and drivers are implemented in collections that are separate packages. So in this case, we're using the Gobot Fermata package. Fermata is a universal serial protocol that's supported by Arduino and other compatible microcontrollers. So it lets you communicate with the Arduino via a serial interface. And then the Gobot GPIO package, that is our general purpose I/O. If anybody here is a Linux user, which if you're not, you ought to be, because that is the operating system of robotics. So the general purpose I/O is where we have all of the different device drivers and things for the, in this case, the LED. So if I can scroll. So we have our main function here. First thing we do is we declare our connection. So we've got the Fermata adapter, and we're going to name it Fermata, and it's going to be connected to dev TTY ACM0, which is kind of the default port on Linux. Then we're going to declare the device, which is an LED, using the new LED and passing along a pointer to the interface of the adapter. That's how the magic of the communication happens. And we're going to name that LED, and it's talking to pin 13. Microcontrollers have different pins. They're usually labeled with either a number or letter or combination. And so in Gobot, whatever it's labeled physically on the board is what you put into your code. You don't have to look up somewhere else on a data sheet. And then last, the third and the most important part of Gobot, the work routine. So the work routine is a Go routine that in this case we have a helper function called every, which is similar to what setInterval does in JavaScript. It repeats the Go routine that's included within it on some periodic interval. In this case, every 1 second, we're going to led.toggle. That's going to turn the LED on and off. And then last, once we've declared all that, we create the actual robot. We say it's got a connection to the Fermata. Device is the LED. Tell it its work routine, and then start. So if the gods are with me. Yes. My universal video adapter.
Can you see that?
Can you guys see that okay?
Okay, cool.
I'm a very bad cameraman. A $5,000 lamp. But you got to start somewhere. All right. So moving on. The BeagleBone Black. Who here knows about the BeagleBone Black? All right, good number of people. They actually sell them at Radio Shack now, which is why nobody can order them online, apparently. Who knew? The Shack is back. So the BeagleBone Black is a single-board system-on-chip Linux computer. It's powered by an ARM processor. It has 68 different general-purpose I/O pins. So it's very, very powerful capabilities in integrating with I2C peripherals or inter-chip peripherals. If you're a board designer, that's how you go about doing your business. You pick your processor, you pick the different chips that are going to support the I/O that you need, and your job is really to integrate them together. So we're going to show the same exact code, pretty much. My cursor will go over there. All right, so once again, we import the Gobot package. We import Gobot BeagleBone, which is the adapter. Remember, we have adapters to communicate with different hardware platforms. But then you'll notice we again import Gobot GPIO. So it's the same drivers, but with a different adapter. And then here's our main routine. Once again, we declare the BeagleBone in this case as the adapter. The same code we saw as before with the LED, except in this case, it's talking to pin P9_12, because that's what it's labeled, but it's still just a digital input-output pin. And then we're going to do one other little extra trick. Remember I told you how there was an API? So we're going to actually launch the API on port 3001. That way we can access it. And then we declare our master, add the robot to it, and then start them all out. In this case, it's just one robot. So let's go to the video. So this is running entirely off the BeagleBone Black. Adrian's just SSH'd in, I believe.
Yeah, so in the Arduino example, we were communicating to the Arduino through my PC. In this example, the BeagleBone Black is actually running the code on the board itself, communicating to its built-in GPIO. So you can either remotely control a device, or if you have a single-board Linux computer, you can control the GPIO from within and design your firmware using Gobot that runs on the device itself.
So now we told you that we had an API, but we also have a complete universal user interface for robots that's written as a single-page AngularJS app, which is embedded right into Gobot. So similar to your router, has a configuration page. That's not how you actually use your router on a daily basis, but when you're developing robotics code, well, obviously, like in my case, my code is always wrong, but where is it wrong? That's the important part. So let's take a look, and hopefully this will actually launch. Oh, yeah, that's right. I hate being dyslexic and doing this. All right, so now this is actually talking to the BeagleBone. So we see the LED. And so let's send it some commands.
So
you can't see the video.
Yeah, well, you guys can see it's still blinking, right? So this is the work routine that's running on the BeagleBone Black. Then when he executes the toggle command through the web interface, it strobes the light faster.
This is up to my pay grade. So as you see, and if we had 10 different robots with many different devices each, we would just navigate the same interface. So it's just a way for us to verify the functionality and to control it. All right, moving on. Okay. All right, well, this is the time when you get to choose your own hardware adventure. What does that mean? It means we're giving away cool stuff. Woo! So all you have to do is go to the Twitterverse. So to win an Arduino starter kit, which includes an Arduino pre-programmed with the Fermata protocol, some wires, a breadboard, cable, everything you need to get started with Gobot today, just tweet Arduino and Gobot.io. So if you win this, so we're going to do a completely arbitrary random selection, so tweet as many times as you want. All right. Or if you want a BeagleBone Black starter kit, which includes a BeagleBone Black, breadboard, jumper cables, wires, and SD cards so that you can load up the Debian image as opposed to using the Angstrom Linux that's built into it, tweet BeagleBoard.org and Gobot.io. BeagleBoard.org and Gobot.io. If you want to win a Sphero 2.0, which you've seen us rolling around out there, then tweet GoSphero and Gobot.io. And then last, if you want to win a Pebble smartwatch, which we are just adding support to Gobot for right now, and you could help out, hint, hint. You could win one of these just by tweeting Pebble and Gobot.io. So those tweets again, Nick, tweet Arduino and Gobot.io to win an Arduino. Tweet BeagleBoard.org and Gobot.io to win a BeagleBoard Black. Tweet GoSphero and Gobot.io to win a Sphero. Or tweet Pebble and Gobot.io. All right, on with the show. The Sphero. Okay. Back to the codes. All right, so a bunch of you have been seeing us roll around Spheros. Oh, whoops. A bunch of you have been seeing us roll around Spheros. My keyboards are not connected. There we go. So what we're going to do now is we're going to actually do something quite radical. Who here knows Conway's Game of Life? All right, most people, more than usual, about 2/3. Let's just do a quick review for those of you who are not mathematically inclined. So there was a man named John Conway. Not John Connor. That's a fictional character. John Conway, a man obsessed with seemingly simple things. For example, flights of seagulls. And he noticed that seagulls don't seem individually very intelligent, yet they're able to fly together in these formations. How on earth could this be possible? And he began to study this. And he created a new field of mathematics, which is known as cellular automata. And Conway's Game of Life is normally played on graph paper. So you have cells, which correspond to these dots, and then you have spaces, which are the squares. And the rules are very simple. For each cell, if it has less than 2 neighbors, it dies from loneliness. If it has exactly 1 other neighbor, then a new cell is born in the blank space. And if it has 3 or more, then it dies from overpopulation. So the first move might start with this, and then the second one looks a little bit like that. All right? So we thought we'd like to do Conway's Game of Life, but with robots. But we realized there was a few little problems if we were going to use the Sphero. The Sphero has no optical sensors. So how can we actually determine our neighbors? Well, thanks to the mathemagic of what is known as the inverse Fourier transform, we can basically take a slice of time and separate it and determine, based on the frequency of each collision, approximately how many neighbors we have. All right, got that? Cool. Oh, wait, but the code. The code. I swore there would be actual code. All right, so once again, we import the Gobot library, which we need. And in this case, we're going to use Gobot Sphero. So we declare a struct with our Conway data. Are we alive? What is our age? How many contacts have we had? And then a pointer back to the Sphero driver of which we belong. Then our main function, we declare our master because we're going to need a master to coordinate the activity of all these different Spheros. We declare an array with the ports of all the different Spheros that we're going to communicate with. Then we actually declare within each of them the adapter to the Sphero. Which port is it going to be? Whichever port we tell it. Because remember, this is a swarm. We're using the exact same code on all of the robots simultaneously. And then the work routine that we're going to do, we declare our Sphero. Spheros are born. On every collision, we note that there was a contact. And this is where you're seeing our evented syntax. Then every 3 seconds, if we're still alive, then we move. Every 10 seconds, if we're still alive, we have a birthday. Life is hard and short in Sphero land. And then we add all of our different robots to the array, or the connections, the adapter, and then our work routine. Then lastly, we start them all out. And then here we have some helper functions to reset our number of contacts, register the number of contacts, rebirth if we have zombie mode, which we're not going to use today because we were kind of pressed for time. So little to do, so much time. Wait, strike that, reverse it. Are we alive? Are we dead? And have we had enough contacts? If we have between 2 and 7 contacts, then we're still alive. Otherwise, we die. Rough. So every birthday, we say happy birthday to the screen, and we have rebirth if we've had enough contacts and we're dead. In other words, if you're just sitting there dead and you get hit enough times, you come back to life. It's kind of a weird thing. And then our movement, we move around, and the Sphero, if it's alive, will roll at a speed of 70, which is pretty fast with the Sphero 2.0, in a random direction. All right. So now let's go to the video. So you'll see them all turn a simultaneous color when we connect to them.
Yeah, it's still
connecting. Almost there. Thank you.
Could we get a more aerial view of it?
Yes, I bet we can. That's my maximum altitude. And this way you can see his screen, so you know we're actually doing this. Oh, and they're alive. They're green. Oh, our first death in the family.
I don't think they can. Oh, yeah.
It's a little washed out, but believe me, you'll know death when you see it when it comes in mass. It may be artificial life, but I'm still sentimental. Some of my best friends are robots. Ooh, 2 gone. 2 down, 3 to go. What will happen? I think they're getting stuck. I suspect it's going to be a mass death. Ooh, it's getting rough.
There's just some tough robots, man.
I know, usually they die a lot faster. Only when we're really pressed for time do they, okay, here it is.
A double whammy.
The Last of Us. I think we should put it out of its misery at this point.
I hate to be a murderer, but duty calls.
If we're living in the Matrix and the sysadmin decides to do a reboot. All right, let's move on. So, all right, now it's time to take to the skies to prove Golang's air superiority. The funny part, you think I'm kidding. All right, so now we're going to switch to the AR drone. The AR drone from Parrot, it's probably the most popular quadcopter. Everyone's seen it. So because you've already seen it, we decided we're going to do more than just make it lift off and land. In fact, we're going to show the real power of Go, and in particular Gobot, to run on different kinds of embedded devices. So what we're going to do right now is we're going to pull out our slightly modified AR drone. Now we've added to the AR drone this little device. Can you guys see this? Higher, lower, to the side, a little more to the left. Focus. All right. So this right here is a Digispark. It is probably the smallest microcontroller. It's a USB, similar to an Arduino, but it runs on an AT-Tiny, so it's even less powerful. However, it does have a similar capability to the Arduino in that you can run a serial protocol with it. It's using a fantastic set of drivers called Little Wire from the brilliant Jenna Fox, Bluebee. She's a genius, and she's done a lot of really cool embedded firmware for small devices. So we actually have a Digispark plugged in to the AR drone.
Through its USB port.
Yeah, these have a USB port built in. And so what we're going to do is we're going to use Gobot running on this computer to fly the drone, and then also communicate with a separate instance of Gobot running on the on the BusyBox distro that's running on the ARM processor that's part of the AR drone.
The factory Linux that runs on the drone.
So we're going to run two instances of Gobot, one on the computer and one on the drone itself. So meta. If it all works. If you're in the front row, well, you've been warned. Let's just put it that way. I have to do a little plugging. So what we're going to do is let's look at the code real fast. To the code. Sorry, but I can't see very well under the best of circumstances. All right, so let's look at the Digispark first. It's the same thing we've seen before. Import Gobot, import the Gobot Digispark, because that's the adapter. Import Gobot GPIO, because again, that's where our LED driver is. Talk to the Digispark. Tell the LED that it's using the Digispark, in this case on the different pin. And then the work we're going to do is every 1 second toggle, so flash on and off. But that's actually executing on the Gobot that's running on the drone itself. Then simultaneously, the drone's own firmware is running. And so we're going to fly it around. Once again, import Gobot. In this case, import Gobot ARDrone, which is where the adapters and the drivers for talking to an AR drone are located. So declare the drone, and then take off. When we're flying, hover. Then after 15 seconds, land. Then we tell Gobot that there's one robot, those are the connections, and to start it up. So what we should see, you probably will see it better not with the camera, but instead just looking, is it should take off.
Well, let's just put the camera over here.
All right.
For those in the back and sides.
And of course, all our internet friends.
There you go.
All right. Good. So what's going to happen is it's going to take off, and then he's going to use the Gobot API to then tell it to start flashing in the same fashion that we were doing before. It's going to be toggling, and then you're going to curl it to...
Yeah.
OK, and then so he's going to just send curl commands to use the RESTful API to make it flash a little crazily so that you know we're not making this up. If we were making it up, we would go a lot smoother. All right, so now we have 2 instances of Gobot running 2 Gobots, 1 drone.
So you can see that even while it's still not flying, but I have API access to the drone. So using the Gobot program that's running on the drone itself, I have independent access to I/O that's completely independent from the onboard firmware that's running on the ARDrone.
But let's keep going. We've got even more. So what about OpenCV? So OpenCV is an open source computer vision package. It's really a complete environment platform all to itself. It's incredibly powerful, and there's a lot of capabilities that have been added to it. We thought we really needed to be able to do some cool things ourselves. So let's take a look at some code. All right, so we have a little more code here. We're importing the Go OpenCV package because we needed to make a few tweaks. And package management in Go is still an evolving frontier. We import Gobot. We import the Gobot ARDrone. And we import Gobot OpenCV. Then we bring in a few more packages that we need to do a few calculations. So the main function here, first thing we're going to do is we're going to load, you can't really see it, but we're going to actually load an XML file that contains the training set for our facial recognition algorithm. Right now we're just using kind of a generic face, but we could train it to individual people's faces, Mark.
Mark Bates, everyone.
Creator of Metacasts and test subject, target, participant.
You should be good, like, right here. Stand back a little
Yeah, it should be fine, really.
You should survive.
All right, so,
I love them.
so while we go through this real fast, we declare the OpenCV adapter. Then we have 2 drivers. One is going to display a window so that we can actually see what the drone sees. And then the other is going to connect to the camera so that we can do our vision processing. Then we declare the adapter for the drone and the drone's driver. That way we can fly it around. Then the work routine. First, we're going to take off. Then, as each frame comes in, we're going to display it in our window. Then, as the drone is itself flying, after 1 second, we're going to kick up to face level, if you will. Then we're going to hover and start our face detection algorithm. So the Go routine that it's going to do is that it's going to hover. Then we're going to clone each image so that we don't end up with a pointer to the exact same image data. Then we're going to use OpenCV to detect the faces, or face. And we're going to target the biggest face, which is why we chose him. So if there's no face, if there is a face, there we go. If there is a face, we're going to draw a rectangle around it so you know who it's targeting. Looking at. And then if he tries to get away, turn, move, evade, it's going to turn with him. If he's going to one direction, it's going to turn clockwise. If the other, counterclockwise. And then we're going to show the image. And then we have to give it a little pause because just Go is so fast. What a great problem. And then after 20 seconds, if he's still alive, it will land. Actually, it'll land in either case, but confidence, man, confidence. All right, and then last, we declare our connections, devices, and work, the same exact pattern we've used, and then we start it out. So now we're going to point our camera at Adrian's computer with our universal video adapter. That way we can see what it sees. More or less. And there's the window. Not seeing any bit. Oh, there we go.
Yeah. Here. Yeah. Here we go. It's a little too slow. Here we go. That's it.
But that's not all. So now we're going to go where every human has gone before. So we're going to show an AR drone, and we just recently added support for the NeuroSky MindWave Bluetooth electroencephalogram. So we're going to put this on the pilot. So it's not a mind-controlled drone, exactly. Our concept is more like if the pilot seems really nervous, we should turn on the autopilot. Too bad other people didn't think of that idea.
Cool as a cucumber.
All right, we're fine. We're going to be fine here. We're all fine.
How
are you? All right, let's see here. So this is what we're going to use to fly the drone.
Yeah, we got a PS3 controller, DualShock 3.
Is that the real one? Yeah,
Yeah.
That's a real one. Not
We
like...
splurged for Gopher.
So we're going to declare the adapter to communicate with the joystick. It's of the type PS3 because we also support Xbox 360 and possibly some other ones soon. We declare the driver for the joystick. Again, same code that we saw before, the ARDrones adapter, the driver for the AR drone, then our work routine. You're starting to see a pattern for me here. So we're going to reset the sticks, the left and the right stick. When the square button is pressed, we take off. When triangle is pressed, we hover. When X is pressed, we land. This is entirely manual control. Left X will control the turning left and right. Right X will control pivoting right and left. Then every 100 milliseconds, we read the stick, because Go is so fast, if we responded to every single joystick event, the drone would not be particularly controllable. So then every 100 milliseconds, we check the stick, and depending on its position, we make adjustments to the drone. Then, once again, every 100 milliseconds, we check the other joystick. That way we can actually land even if we lose control of a joystick because it breaks on us because we got really nervous and we moved it too hard one direction or another. And then a few healthy helper functions. So then the last thing is we promised you brain waves, and so brain waves you shall have. So we have, again, we import Gobot. We're going to use the Gobot NeuroSky, or Neuroshki as we call it, after being in Poland recently. And then we're going to read this data, and then we're going to read it back from the API. And if all goes well, let's see.
Yeah.
So far, so good.
Are you connected to the
Oh, yeah, I got
conference Wi-Fi?
That would help, huh? Which one should I be connected to?
Try Dead Zone.
Okay. We have to connect to the correct Wi-Fi access point. This would be a good time to tweet. Hint, hint. All right. Hopefully. All right, that's his brain on Go. It is a gateway of sorts. An IP gateway. All right.
So then you want to just point the camera at the drone? So.
Yeah, but we won't be able to see it.
Oh, yeah. Well,
we're going to look at his brain while he flies the drone. Let's see if he gets nervous. I mean, it is free flight. Standing by. Standing by, Houston. All right, so we're using Gobot to fly the drone, and we're checking out the pilot's mental state. Seems kind of erratic to me. But I'm not a neuroscientist, so I don't know what I'm doing.
usually I pan over the audience, but I don't want you guys to see how nervous I am to do that. I feel self-conscious right now.
This whole time I thought you were so confident.
I am. Oh, no.
All right, I think we better land it.
Yeah.
won't stop. His brain won't stop.
I'm too jazzed.
I guess that's good. I can't tell. Do I have another window open somewhere?
I think it's in a different tab.
I bet you're right.
I'm thinking.
Hey, hey, hey. So was that fun? I think fun is underrated. You know, that's one of the times when we're most intellectually engaged is when we're having fun. So we want you to join the robot evolution. That's why we're here. So Gobot.io, all of this is open source, if we forgot to mention that. It's kind of important. It's all open source. It's all Apache 2.0 license, so you can grab it, use it, build a commercial product, continue in the open source vein. No one can take it away from you, my friends. No one can take it away. Channeling my inner Stallman. So Gobot.io, follow us on Twitter at Gobot.io, which you probably know because you've been tweeting like mad, so you win one of these cool items. And thank you very much.